Hello, I'm demonstrating the final project for my digital logic laboratory. The project is for the FPGA, and I decided to create a VGA controller that would output to a VGA display a sort of type of video game with very basic collision detection and very basic user input. Um, as you can see right here, I have the FPGA with a VGA connection. It's from the Basys 3 board, which already has a VGA circuit already integrated into it, so I didn't have to build the circuit all by myself. And it's being connected to the display up here. Um, Before I started the project, I needed to first understand how VGA display worked. And the way a VGA display works is that it draws from the top left of the screen horizontally, and it goes down pixel by pixel. So it goes horizontally one line, and then it goes down by one pixel, and then it goes horizontally again. So for you to create the VGA driver, you need to pick a resolution you're going to do it at, and a refresh rate that you're going to do it at. And for this project, I chose 60 hertz refresh rate and a 640 by 480 display. So it's 640 pixels wide and 480 pixels in depth. And I'm going to show you what I got right now. Okay. As you can see on the screen is just a very basic uh, black dot, which is what the player, I guess, controls, and you control it through the buttons on the FPGA. And it's kind of like Flappy Bird, so it it you have to go through the pipes. And if there's a collision that happens with the block or the pipe, and then so it stops, and then you would have to press the center button to reset it over again. So since I ran into the block, I have to reset it. Uh, it's actually pretty difficult too. Um, so yeah. So I chose a 640 by 480 display because it was the simplest display resolution you could do, and it's very simple to create a clock with this board specifically to facilitate that resolution, which was a 25.175 megahertz clock. But since I really didn't create a 25.175 megahertz. I just created a 25 megahertz clock. So the error in the pixel rate wasn't that significant, and the display turned out pretty normal, as you can see. Every time the refresh or the reset button is pressed, there's also a flash on the display of the resolution, and I'm going to show that to you. Up here it says 640 by 480 at 60 hertz. So that's my display of the VGA. I was originally gonna implement more ideas into the project, but unfortunately I ran out of time and I wasn't able to. And one of the things I was gonna implement was like adding color to it. Another thing I was gonna implement was like adding a counter that would count every single time you pass the pipe. And another thing I was gonna implement was a game over screen. So I wasn't able to do any of it because I wasn't able to budget my time properly. But hopefully in the future I can maybe work on it some more. Other than that, this project was very satisfying to do, and it was very difficult. Now I'm going to explain how I wrote the Verilog code in Vivado, and I'm going to use a screen capture to show you. Thank you. Hello, now I'm going to explain the Verilog code in Vivado. Okay, so for the top module, I instantiated 3 separate modules. But instead of explaining this code, it's probably better to look at a block diagram of this module I have right here. In this block diagram, I have 3 separate modules instantiated, and you can and also the inputs and outputs to the top module. So the outputs are basically go to the VGA display, which are the H-sync and the V-sync lines, as well as the RGB lines, which are the red, green, and blue ones, which are all 4 bits each. That basically is what sweeps across the screen when the time, depending on the time constraints of these modules. As far as the inputs, I got 5 different button inputs in here, which all input into separate modules. The first module that has an input is the clock divider, which creates a 25 megahertz clock, which feeds into the VGA display driver. And that display driver outputs 3 signals that get inputted into the module called output. The horizontal counter and the vertical counter registers are both 10-bit lines that count the horizontal pixels and the vertical pixel. And also there's a video on. And then the output determines what to output depending on what the player, which buttons are being pressed at the time. So this is the first module that gets instantiated. It's the clock divider module, and it's pretty simple. There's not much going on here. It divides the 100 megahertz clock and creates 2 different clocks for the 2 separate modules that I'll explain later. The VGA driver is a little bit more complicated. It's basically got 2 inputs and 5 outputs. And to better explain this module, it's probably best to look at this picture. So this picture shows you the timing diagrams of a normal VGA display. The normal VGA display usually has these timings happening right here. The horizontal thing has these things called the front porch, the signal pulse, and the back porch, which basically constitute a buffer zone that the pixel clock has to go through in order to properly display here on the actual display. So your display is only being counted in here in this display area, but this blank time is basically a buffer zone so that every time it refreshes and it goes back up to the next line, it has enough time to make it over there. So it does not. So it's basically a buffer. And you have to implement this in Verilog to get your VGA Verilog code to work properly. So that's what I did. I got the, I found all these parameters. I found them online because the VGA timings are industry standard, and you can just look up all these pixels depending on your refresh rate and the resolution that you're going for. So you just basically can plug these numbers in and make sure that the horizontal counter and the vertical counter, which are these 2 registers, cross at the right time and at the right rate. So that's basically what these parameters are doing and what these always blocks are doing. This always block and this always block are doing the horizontal counting and the horizontal sync pulses of the horizontal counter. So it's doing the horizontal counting and then horizontally again refreshes. And then these 2 always blocks are doing the vertical lines. So for every vertical line, these get incremented, and then this sync pulse gets pulsed at the right time. The last part of this module is the display on, to determine the display on. So like the last picture showed, the display on is actually only a certain part of the screen, not the whole screen. So this ensures that if the counter is within certain parts, that the display on line is asserted. This means if it's within the right boundaries, display on is 1, and if it's not in the right boundaries, display on is off. Okay, so that's VGA driver. The output driver is also pretty complicated, but it's the game. It's basically the game logic and the the display logic of this whole project. So it keeps account. It keeps an account of the variables of the positions, X and Y positions of the boxes, and X and Y positions of the pipe that scroll across the screen. So, I got three different pipes, 3 instances of pipes, and they keep getting refilled over and over. As they disappear to the left side, they return back around from the right side, and it just keeps going over and over again. That's what these are. These are the X and Y coordinates of those pipes. And this is the X and Y coordinate of the box that the player controls. These are the just local parameters for you to be able to tell the screen bounds that are being drawn into. And the first always block right here, it's a really big one, controls it updates the box and the pipes X and Y coordinates at a cycle at every positive edge of the clock. So it's constantly updating basically the X and Y coordinates of those boxes. So that if a collision happens, the game stops, and you have to press the reset button to start over. And that's basically what this is doing. I'm not going to get into too much detail because there's a lot of it, but that's what it's basically doing. It's updating constantly, and it pushes also the pipes from the right side to the left side, and it keeps updating over and over again. And then this last piece right here is how I calculate what colors to output to the screen. I originally was going to output several different colors, but I ran out of time and I wasn't able to do it. So the only 2 colors I came up with was black and white. Was the easiest colors I can think of. So, basically this always block is what it is. If it as the pixel counter goes from the left to right horizontally over and over from top to bottom, drawing frame by frame, as it hits the positions of the pipes or the boxes, if it hits it starts drawing black, and if not, it'll draw a white color. That's why I have these RGB, the red, green, blue values are either completely turned off or completely turned off. So completely turned off would be black, and completely turned on, so all ones, would be white. So that's why there's a white background and a black contrasting like foreground. And that's pretty much it. That's how I display to the output. There's nothing else. This is the constraint file, but the constraint file is found in the report. And the top model basically just ties all of the modules together. And thank you for your time. That was it.